Calculus 2.
Eventually.
Hey, I want to play some spinning rap.
Hello and welcome back to Calculus 2. Section 8.4. We have 3 tests to cover here. Divergent test, integral test, and P-series. So now we have the 3 tests that, well, are used to test convergence, divergence. Now, guys, the first test we are covering is called Divergence Test. So please never, ever, ever, ever write that something converges by divergence test, because they just listen to the silliness of that statement. All right, it's like telling someone, you know, I don't know, you're short because you're tall, or you're skinny because you're fat, or whatever. Like, it makes no sense. All right, so we're starting with divergence test. And the theorem is very simple for this one. So if series of AK converges, then limit of AK as k goes to to infinity, sorry, is 0. If limit of k goes to infinity of AK is different than 0, then summation of AK diverges. So generally, it's the first part of this theorem that confuses people and probably leads them to write some really silly things. You know what? Just you can just cross off the first part, and it won't do anything to your entire knowledge base. All right. The second part of this statement is the one that we need to observe. So to start this off, when I write summation AK or AN or AM, whatever you use, doesn't matter, we are going to take a look at this part, right? And that part is called the sequence. But then you take a look at everything, and it's called series. You should never look at the sequence and make conclusions about series, because that's very dangerous. Except in the case where you are looking for divergence. So technically what it says, that if the limit of the sequence is not 0, then the series definitely diverges. That is something that it's given. So now we can test this. We should be able to solve certain problems in multiple ways and always have the same answer at the end. So if I have summation of, let's say, 3 times 6 to the n, and n starts at 0 and goes to infinity, we should quickly note that by geometric series this diverges. Yes. So your R is equal to 6. 6 is bigger than 1, and that's divergent by geometric series, right? So this is your full answer, 100%, right? Credit, all of that done, right? So that's that. But now in this case, we can also take a look. We can take a look at the limit as n goes to infinity of 3 times 6 to the n, and you will see that answer for that is infinity. right? Because if n goes to infinity, 6 to the n goes to infinity times 3. So it's infinity, which is not 0, which leads to the same conclusion at this time by divergence test. Now, divergence test on the sheet that I gave you is called nth term test. So if you read different books, or if you look at some of the lectures online and so on, you might run into a person calling it nth term test rather than divergence. So that's the same thing. So now, growth rate of functions could greatly help you figure out whether you have a divergent series. Or let me write this in blood. Never claim convergence using divergence test. This should be common sense, but yeah. And if you look at the sheet that I gave you, the convergence is empty. Yes?
So if it doesn't diverge with this, we use like...
You have to do something else. It's
like,
inconclusive.
We use like one of the other things to...
Yes. So that is something that you have to really be careful about. And I'm going to give you an example now of, see, the summation of 1 over n, where n, let's say, starts at 1, goes to infinity, right? So you look at this series, and if you try to use the limit as n goes to infinity for 1 over n, you will get 0. Right? You are getting 0. However, all this says is that divergence test is inconclusive. That's all it says. Now, I will tell you the answer for this. So this series is divergent by integral test or P series, whatever. So we know, we haven't covered these yet, they're next. But the series that you see here, 1 over n, is called harmonic series. It's used a lot. And it's a divergent series. And you see that our divergent test was inconclusive on it, actually. So, you know, be very careful with this test. If you see that the limit is equal to 0, you immediately have to move on. So if you see limit equal to 0, you immediately move on because test is inconclusive. When the limit equals 0, you can still get divergence. Here's the example, right? What is guaranteed by the theorem is that if the limit is not 0, so you get 2 or a half or a pi or infinity, then it's guaranteed that the series is divergent. So, if the limit is 0, it could be convergent or divergent. So the test is inconclusive. If the limit is different than 0, it's definitely divergent. So you will say diverges by divergence test, which makes sense to write. You can also call it nth term test. It's fine. It's on the sheet. Yes?
So this is something that we would look to do right away when we see the problem.
Amazing. Perfect. So when you are faced with problem, you first determine which type of the test you are going to use. Just like you had the derivative, oh, it's product rule, or integral, oh yeah, this is integration by parts, right, or U sub. So when you have an exam, and on that exam you have, I don't know, 10, 15 of these to test, divergence test should be immediately applied to all of the problems. because, one or two of those are bound to have a non-zero limit. Immediately knocks off those two problems from the list, and divergence test, right, and you're done with two problems. So divergence test is something to be done first on every series problem to see. Now, obviously, for vast majority, the limit will be 0, so the test is inconclusive. So for vast majority of problems. But then, for those few, you will be able to use it and then, right, immediately claim divergence because limit will be non-zero. So for the last time, if the limit is 0, test is inconclusive, move on. If the limit is not 0, test is definitely telling you that a series is divergent. That's that. That's the divergence test. So you are learning that one sentence and just very careful to use it the right way. Integral test is next. For integral test, you will have to check the conditions before you get to do integral test. First off, the area of mathematics that we are at right now is discrete. That's a point, plus another point, plus another point. You can't integrate that with the integral that you know. There is something called Lebesgue integration later on. Probably guys in the back already know about it. So Lebesgue integration is the one that integrates dots like this. Now regular integration from your Calc 1, 2, and 3, I cannot integrate anything in this chapter. However, what we can do is we can connect those dots with a function. Kind of fill it in. And then you can integrate the function. If the area under the curve converges, then if the conditions were satisfied, the series would converge as well. And if the area diverges, area under the curve diverges, then the other one diverge, series would diverge as well. So the key point for integral tests is this transformation from the world of discrete mathematics where you have the dot inputs, right? So input is just 1, 2, 3, 4, to a continuous input which is interval based. So to give you an example of this transformation, on this side I'll have f of n. Now f of n is given as an in our case. So if I say that an is equal to, let's say, n squared, then I get to draw zero, 1, 2, 3, let's say. I get to draw 0, 0 dot, 1, 1 dot, 2, 4 dot, and this dot. So you see the 4 dots, 4, 0, 2 through 3, right? And this would be your axis n, this would be your an, right, as the answer. So this is the world of discrete. Now we say this is going to be pushed into the f of x realm, which is equal to y, in which case our y will be x squared. And we know that that will produce a line, quadratic, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So the difference between the two is clearly the space in between the dots. On your discrete side, which is what we are dealing with now in chapter 8, we just have these dots. There is no area under the curve because there is no curve. right? It's just random dots, values, x and y values, right? In this case, n and an values. You can't integrate that. You can't do anything with it right now. Now, you want to know whether it's convergent to divergent. So what you do is you say, okay, I can make, hopefully, the one-to-one correspondence between our function an, discrete function, and our function, right, f of x. So technically what you are doing is just filling in the blanks, right, in between these. You're smoothing up the curve. Now, this is a dangerous business because the three conditions must be satisfied, and only if all three conditions are satisfied, you get to transform your fn into fx. So now, the three conditions are that the function has to be positive, decreasing, and continuous. Those are the three rules. And clearly, every time you need to do the integral test, you actually have to prove those three. So this is an integral test that is known for its carpal tunnel developing kind of tendencies, because it takes a long time. You have to do three proofs, and then you do integral test, and then you finally write your conclusion at the end. So they tend to take a page or longer. So let's take a look at this, what I called harmonic series before. I want to, let me write the theorem first for the integral test. So, conditions. If all of the conditions are met, then the integral and the series both converge or both diverge. Conditions are number one, you can say continuity. Number two, conditions. Okay, let's rephrase this. Conditions. Function, so f of x needs to be, and here we go, number one, continuous on a to b. Number two, it has to be positive, and number three, decreasing. So this is the integral test. So integral test is going to take your an, transform that into f of x, and then you get to do improper integral because your input was, let's say, 0, right, for the summation, 0 on the bottom, infinity on the top. Well, those 0 and infinity become limits of your integral. So you are always working on the improper integral of first kind, right, type 1 improper integrals, because you will always have whatever number is on the bottom to infinity on top. So you're always using that, you will always be using that limit b. So now, if these conditions are met, if the conditions are met, then you are allowed to, instead of solving series, you solve the integral, and then they both converge or they both diverge at the same time. Now it's time for us to take a look at the problem with series start n at 1 to infinity of 1 over n. So this is called harmonic series. Harmonic series, as I said before, will end up diverging, even though 1 over n is convergent, right? As a sequence is a convergent, but as soon as you add sum to it, it actually diverges. So we are going to prove that this is divergent series by cranking the integral test. So now we're going to write that an is 1 over n, which means that my function f of x is going to be 1 over x. And that's going to be on the interval 1 to infinity, right? It's a Klopen interval. Klopen means closed on one side, open on the other, right? They're also called half open and half closed, but Klopen is much funnier word. So this is what I need to get my conditions, right? So check conditions. Check 3 conditions. If the 3 conditions hold, then you are allowed to integrate 1 over x. If one of those conditions fails, you cannot use this test. It's very simple. All right, let's go. Condition number 1. What did I say? Continuous? Okay. Continuous. So is it continuous? Well, you have to make sure that the function is continuous on the interval provided. If you draw function 1 over x, you know that 1 over x is discontinuous at 0, right? There's a vertical asymptote there. Look at the graph. However, you don't care about that because your interval starts at 1 and goes to positive infinity. Right? It's right there. So if it goes from 1 to infinity, and guys, you will always have the interval because you have these guys on the sum, right? You have that on a sum, so that gives you the interval, and you have the interval, so you will always be able to look at the part of the function. So on the interval, one to infinity, 1 over x is continuous. And we don't care about anything before 1. Yes, there is discontinuity at 0, but who cares? We only care about the part of the line that we actually need. So, continuity, pass. Green check mark. There we go. Number 2. Positive. It is also easy to see that the graph is always above x-axis. So all of the y values, the entire range, consists of positive numbers. So is it positive? Green check. Yes, it is positive. And I'll write the rationale. Yes, because 1 over x on, and I have to put 1 to infinity again, is always positive. Technically what you're doing is, since your input are positive numbers, you're dividing, well, okay, domain consists of positive numbers. Only. So 1 divided by a positive number equals positive number. So our proof that the function is always positive is right there. You are dividing two positive numbers at all time. So the first part up there says the interval, right, needs to be continuous. It is continuous on the interval. The second one says it needs to be positive. The third one is decreasing. All right. Is it decreasing? Again, you look at you look at your graph. If you have the graph, you can see the values are decreasing, and you claim, yeah, it's decreasing because. But what do you do if you don't know how to graph? And remember that you do not have access to graphing calculators on the exam. So if you don't know how to graph, then what can you do?
You take the limit of it?
Nope. Limit does not give us whether the function is decreasing or increasing. Which concept in calculus did we learn? Yes? Yes, derivative. The first derivative test, as a conclusion, has that the function is increasing or decreasing. You see, there's a reason why Calculus 1 is prerequisite for Calculus 2. The continuity calculations were in Chapter 2 in Calc 1, and now we have to deal with first derivative test, which is your Calculus 1, Chapter 4.2, I believe. So we have now decreasing, and to check if the function is decreasing on the interval 1 to infinity, we can just run the first derivative test. So use first derivative test from Calc 1. All right, let's use the first derivative test. The first derivative test says you have the function f of x, which is 1 over x. Then you take its derivative. It becomes negative 1 over x squared. All right. You set this equal to 0. You get no solution, right? But you also know that there is a vertical asymptote at x equals 0, which stays preserved. So now, when you do your partitioning, you will partition from negative infinity to 0 and 0 to positive infinity. But again, we don't care about anything to the left of 1. So we're only going to consider the region afterwards. Now what do you have? In this region, you only have positive numbers. No coffee. So now, if you have positive numbers, the first derivative test states that you are supposed to take your test point and plug in the first derivative and see if you're getting positive or negative number. If you're getting negative number, it's decreasing. If you get a positive number, it's increasing. So, pick number 2, let's say. So, x equals to 2. So, f prime, computed at 2, is negative 1 over 4. So, that's negative 1/4. That's less than 0, meaning decrease. And that's exactly what we need to show. So, decreasing, check. Yes, done. All conditions, let me write in green. All 3 conditions hold. That means that series n goes from 1 to infinity of 1 over n, and integral 1 to infinity of 1 over x dx will have same conclusion. So, what are the troll questions look like for the exam? Well, one of the 3 conditions is not satisfied. For instance, a vertical asymptote, right? If you don't know that, I don't know, 3 over x minus 5, 3 over x minus 5 has a vertical asymptote at 5. If my series starts at 1 and goes to infinity, well, 5 is definitely included in that. You see? So it's not continuous. Right? Continuity is ruined, therefore we can't use the method. What function is not decreasing? You know the example where I showed you the connection between the discrete and continuous world? Which function have I used? I used x squared, right? I used x squared. It's right here. Is it continuous? Yes. Is it positive? Yes. Is it decreasing? No. So you can't use it, right? Condition failed. So you have to prove all 3 conditions, and only if all 3 conditions hold, then you get to write the integral from 1 to infinity of 1 over x dx is equal to, and you go on to solve it. This is your type 1 integral. Therefore, you have to use the limit procedure. So limit b goes to infinity, integral 1 to b, 1 over x dx. What is the integral of 1 over x? Very good. ln absolute x calculated from 1 to b. So this becomes limit b goes to infinity of ln of b minus ln of 1. ln of 1 is 0, so that dies. We only have ln of b. But ln is the increasing function. You plug in infinity, the answer is going to go to infinity, so infinity. Diverges. Integral diverges. So now, here's the answer. This is what you get your grade for. Answer. Since all 3 conditions hold, and the integral 1 to infinity of 1 over x dx diverges, series summation n goes from 1 to infinity 1 over n diverges by integral test. If you want full credit, this red sentence must be there. Otherwise, don't worry about it. If you don't want the full credit, just skip that. And maybe a little bit more of the problem and get something wrong. Yes?
So in the step before that final red line, when you decide that ln1 is equal to 0, right?
I didn't decide, that's a fact.
Right. But I mean, you go through the computation. Can
Yes.
you avoid that all? Just by default, knowing that it's a constant, so infinity minus a constant is still infinity?
Yes.
Okay.
Sometimes you will have to use L'Hopital's rule to deal with the limit at the end. It all depends what you get, because it's not always going to be easy to deal with the answer. So this is what the full problem looks like. There is a statement up there, and when you take a look at the statement, you create its continuous analog. All right, you contain its continuous analog, and then you make sure the 3 conditions hold on that continuous analog. So your job now is to do the 3 proofs. When you do the 3 proofs, then and all 3 pass, then you can claim that instead of worrying about the series, you work on the integral. And then you integrate. It will always be type 1 improper. Now, type 1 improper just means you have to have the limit in front. The guts of the integral could be u sub, by parts, could be anything from chapter 7. Right? So, in this case, integration of 1 over x is equal to ln x, that was a basic integral, but you can have a trig sub there, it's fine. Right? So that's that. And you can see that chapter 7 is still very relevant on the next exam. So now I want you to focus on and try this, repeat all of these steps for series. Let's start it at, let's say, 2 to infinity of 1 over n squared. Make sure you end with a sentence. Yeah, I'll give you some time to figure this out because you have all the steps. It's just a lot of work, so take some more time. What happened? You're hungry. Cookies are right here. Keep working, keep working.
That's the whole thing.
That's a big stretch.
Does this look cleaner than it did before?
Oh,
you're playing heroes?
Yes,
You're doing events? These dailies?
Yeah, I'll be right there. All right, make sure you have the sentence at the end.
I'm not hearing the first word, man. It's like something dope. saying the same words, and then you're not saying anything.
Everybody, well, I know I'm done. License. No, it's not. It's or work.
What? Final answers to what's final answer? Oh, final answer.
All right, let's take a look at this problem together to go through all of the steps. As I said, integral test is going to be a little bit of a carpal tunnel thing going. So we look at an, which is 1 over n squared, and export that into f of x is 1 over x squared on 1 to infinity again. No, 2 to infinity, sorry. 2 to infinity. Now we check our conditions for f of x. You can do the conditions in any order, it doesn't matter. So continuous. We have to say yes, because you have division of two polynomials where denominator cannot be 0. Yes, because both 1 and x squared are continuous, and their quotient is continuous because denominator doesn't equal to 0 on 2 to infinity, right? It is equal to 0 at 0, but 0 is not the part of our domain, so there you go. It's continuous. Number 2. Guys, I'm pretending that I don't know what the graph looks like. I do know what the graph looks like, but I'm pretending that I don't, so I don't want to cheat off of the graph. I'm just going to use all of the calculations. The next one is positive. Is it positive? Well, yes, it is. Yes. Because x squared is always positive, and quotient of two positive numbers is a positive number. So number 1 is always positive. X squared will always be positive. Positive divided by positive is always positive. So yes, function is always positive. 3, decreasing. Again, if you are to draw the graph, it will be clear immediately that it's always decreasing. But then we can do the first derivative test and show it's decreasing because the first derivative is equal to, remember, you are differentiating x to the negative 2. It's going to be negative 2 over x cubed, right? So on, again, 2 to infinity. So when you consider the derivative on 2 to infinity, every number in a domain is positive. You always have negative divided by positive, right? So every number of 2 to infinity is positive and negative 2 divided by positive is equal to negative. Therefore, the derivative is negative everywhere on 2 to infinity. So f of x is decreasing everywhere on 2 to infinity. These, proofs, they don't have to be word for word what I'm writing, as long as you are logically came up with the conclusion that you were supposed to have. What is the correct conclusion? It's fine. You can word it differently. You will write whatever. You will find your way. So now I know that all three of these conditions are satisfied. Therefore, I can go and say integral 2 to infinity of 1 over x squared dx, and I can work on this integral now. So this is going to be limit b goes to infinity, the integral from 2 to b of x negative 2 dx. So this is limit b goes to infinity, and now we have the integral of x to the negative 2 becomes x to the negative 1. So this is negative 1 over x, and we have our limits 2 to b. So now limit b goes to infinity. When I plug in b, I get negative 1 over b plus 1/2. Now negative 1 over b will go to 0 when you plug in infinity for b, because 1 divided by infinity is 0, and we get 1/2. So that converges, which implies that series of 1 over n squared converges. But we'll write that in the answer. The one that you get the points for. So what's the answer? Since all three conditions hold and integral 2 to infinity of 1 over x squared dx converges, the series summation n goes to 2 to infinity 1 over n squared converges by integral test. So what you see in red is the answer to score the full credit on this question. Takes a long time, right? There are 4 different calculations you have to do. So 3 proofs and then the integral, right? So it's 4 different calculations. And then you're writing the answer. Since all 3 conditions hold, then, right, you can do the integral. Integral converges as well. So the conclusion from the integral test is if integral converges, once the conditions are met, if integral converges, the series converges. Now, what's very important, and I have to write this in blood over here, do not play with fire to say that the series converges to 1/2. Hell no. All right? We don't know where it converges. The only 2 that we know where it converges to are geometric and telescopic. The other ones, when they converge, we have no clue where they converge to. So, series AN does not converge to the value of the convergent integral. yeah, I know it's only -2 for the test, but later on you might see it again in differential equations, and then someone's going to laugh. I mean, if you did all the work and the whole question is like 10, 12 points, and you go at the end and you say it converges to 1/2, well, clearly you don't know that piece, so -2, right? Because that's not true. This one actually converges to pi²/6. You go figure out why and how. So that's the integral test. I would like to do one more integral test, but before I do one more integral test, something from homework that is not as basic as this, right? Something that it's juicier. By the way, the 2 examples that I did for integral test, that's the 2 biggest joke examples that you can get, right? Because functions were joke to integrate, and then the proofs were short and simple because these are really basic functions, right? Let's see something that has ease and inverse tangent and some interesting things that you can enjoy, right? So these 2 problems, are like really bottom of the barrel in terms of the integral test. But before I go further, guys, I need to actually go to P-series because these 2 examples are triggering P-series. And then we'll go back to integral test. So P-series, what I had is summation 1/n, and that was divergent. And then I had summation 1/n², and that was convergent. All right, so these are the 2 problems I just did. I used the integral test, I did all the proofs and calculations, therefore we know that this is true. Now, P-series say the following thing. Summation of 1/n to the p is going to be convergent if p is larger than 1, and it's going to be divergent if p is less or equal than 1. So equal to 1 is the harmonic series. You see it's divergent. Equal is right there. It's divergent. And then n². Now this means 1/n³, 1/n to the 7th, and so on. How about 1 over the square root of n?
Divergent.
Divergent, right? So guys, for P-series, you're just memorizing this statement. There are no calculations here. No calculations. You look at the problem and you immediately know it. Now, where do you trip? Where you trip when the problem looks like it's P-series, but it's not. Like summation 1/2 to the n. Not P-series. That's good enough. What is this? Geometry. That was nice. I said, this is not P-series. What is it? And the answer is not P-series. It's geometry, guys. So please, please, please note the difference in 2 to the n and n squared. All right? So note that difference. One is exponential, the other one is polynomial. So this is generally, right, when the high stress kicks in during the exam, right? These are the things that you have to be very careful about. So the problem you see up there is convergent by geometric series, because you can put n on 1 and then have the n for the entire thing, and then just, right? So that's that stuff. So and this is P series over. They're even easier. This is the easiest probably, because you don't have to do limit, you don't have to do anything over here. You just look. If the form is right, n to the exponent, you take a look at the value of n, or value of p, and then determine whether you have convergence or divergence simply by what the p-value is. So this is the simplest test you have of all tests, all 10 tests. This is the easiest one, followed by geometric series, followed by the nth term test. The integral test probably rates as the most annoying one. It's definitely the longest because it's most computationally, right, intensive and all of that stuff. The proof of P series is given by integral test. They have cases, and then you go, you compute all the cases. It's done in the book. If you're interested, look into it. As I said, it's not an honors section, but it is beneficial for you to learn if you are moving on with math, electrical engineering, and stuff like that. You should know it. Back to integral. So I want to go into the homework and find some of these problems that we can explore. All right, so I'm going to ask you to pick one, and then you can enjoy the others at home. You see the bottom over here? It says 19 through 24. There's more on the top over there, but so pick something 19 through 24. I'm sorry? 19. Pick anything other than 19.
24.
Because 19, guys, 19 is e to the k, right? So 19 is, they did that just to say, yeah, it's not actually, it's geometric series. So it converges by geometric series. There's no need for 19 to use integral test. Maybe you want to write that in your notes now. 19 is solved for you quickly, right? It's geometric series. Geometric series, you don't have 1/2 to the k, you have 1 over e to the k. Don't discriminate. E is a number. Be nice once in your lifetime. Yes.
So if it's 1 over like a e or an a to the n or whatever, well, not a, I guess. Is it, we just put the like the k on the 1 and then pull it out of the thing, and then 1 is a, and then 1 over e is the r, or 1 over the whatever is the r.
Very good. All right, so pick something else. 20? 23. Okay. 23. Summation 0 to infinity of 1 over square root of, I use n's, I use k's. N is faster to write than a k, which is the reason why I like n better. You can use k, you can use m, you can use whatever you like, right? The reason why I use n's, as I said, is just faster to write than a k. All right. So now, what do I have? I have f of x to be 1 over square root of x plus 8. I don't know what this looks like. I know that I need to be on 0 to infinity. And it better not have any of the vertical asymptotes in here because that would ruin the continuity. So I am going to check where the vertical asymptote is so that I can actually do the continuity part. So let's go. Number one, is it continuous? Well, square root of x plus 8 equal to 0. I want to see what is the point that makes everything bad. And clearly that's negative 8. Not in 0 to infinity, therefore we're good. So, yes, it is continuous on 0 to infinity. You see the way I phrase this is I say, yes, it is continuous, but I also say that it's continuous on the interval that we care about. This is not globally continuous, guys. It's discontinuous at negative 8. It has a vertical asymptote at negative 8. However, it is continuous for what we need it for, and that is 0 to infinity. So we're good on continuity part. Check. Number two, is it positive? All right, is it positive? So I can only bring in positive numbers, right? So all x values in 0 to infinity are positive. Positive plus 8 is equal to positive, right? The smallest positive integer is 1, plus 8 is 9, that's positive. So there is no way to make this negative by adding 8. And then square root of positive number is positive number because square root of x is increasing function. Right, we can also provide a little graph over here. Whee!
So we should break down like each of the individual functions.
Yes.
For the positive. Okay.
That is exactly what Calculus2 teaches you in continuity. You have those rules that say if f and g are both continuous, then their sum is continuous. If and a difference and product and the quotient if g is not 0, right? So I'm using that theorem. I'm using the theorem that says that any combination of continuous functions is continuous provided that your denominator is behaving nicely. So that's that. And now number 3. Decreasing. You know what we did so far for decreasing? We did derivative every time. You can actually also use algebra if you don't want a derivative, because other way than the derivative. So need to show that n plus 1 is smaller, that a n plus 1 is smaller than a n. You want the next number to be smaller than the previous one. Right? Does it make sense? Look. If I have a decreasing function, and I have these two values, this is the original one, this is the next one. Next one is smaller in height than the previous one. So you can, if you are able to prove this, then you got yourself a decreasing function. So you can go back and pick 1 over square root of n plus 8, and that needs to be smaller, that needs to be larger than 1 over square root of n plus 1 plus 8. So you are checking to see if this is right. So we can do this, or you can do the derivative, right? Sometimes it's really tedious to do algebra, so maybe the derivative is better and faster. But then sometimes you might just want to shovel algebra around and be done. Yes?
So like, you can just plug in like 1 and then 2? Or...
No, just solve this algebraically now.
Oh, okay.
Simplify it.
Oh, okay, so we don't...
So what I'm going to do is I'm going to cross multiply, and I'm going to get that the square root of n plus 8 is less than the square root of n plus 9. And yeah, done, right? So just by cross multiplying. So it was quick. So we postulate that we want, right, so to have a decreasing function, your next term needs to be smaller than the previous term. So, I mean the value of the term. So all I did is I said, okay, this is my next term, needs to be smaller than the previous term. And then when I cross multiply them, I got n plus 8 is smaller than n plus 9. Right? If you square both, you will just have that n is smaller than n minus 1 if you subtract 8 from both sides. So we got the true statement, and because we got the true statement, when we check for decrease, we know it's decreasing. So now what do we do? Now we do the integral. So we are supposed to, so all three conditions hold. Integral 0 to infinity of 1 over square root of x plus 8 dx. This is equal to the limit x goes to, b goes to infinity of integral 0 to b of dx over square root of x plus 8. So how do we integrate this? U sub, basic U sub, u equals x plus 8, du equals dx, plug everything in, limit b goes to infinity, integral, guys, the limits will change, right? That 0 becomes 8 and b becomes b plus 8, but we can ignore it and then just go back to x values when we're done. This is going to be u to the negative 1/2 du. So limit b goes to infinity. It's u to the 1/2 divided by 1/2. It's good. What did we talk about? From well, we have to go back to the other to x. So b goes to infinity 2 times, and then you have a square root of x plus 8 computed from 0 to b. So what do I have? I have the plug in b. So this is going to be limit b goes to infinity. Plug in b, we have 2 times square root of x minus x plus 8, minus the next term is when I plug in 0, so it's just 2 root 8. That's infinity, diverges, so series diverges by integral test. When you plug in infinity for x, infinity plus 8 is infinity, square root of infinity is infinity times 2, still infinity, infinity minus 4 root 2 is, 4 root 2 is like 6, alright? So you have this. And that's done deal. Now, can anyone just think for a bit and it might be tough, but tell me, why did I know immediately, as soon as I seen a problem, why I know this is a divergent problem? Divergence test doesn't work. Don't even try it. The limit is 0, so that's it. Yes?
Is it the P series?
Yes. We did not learn this technique yet. It's called comparison test. That's next lecture 8.5. Right? Now, probably we'll deal with those tomorrow because we still have root and ratio to get there. But when I see the problem, you know, in my head, I erase all of the unnecessary things, and the unnecessary thing here is +8. So if I erase that +8, this problem becomes 1 over n to the half. And 1 over n to the half is the P series. So you will be comparing this in a comparison test. You'll be comparing this to P series 1 over n to the half, and if that satisfies conditions and things, then you would also see divergence there because P series of n to the half diverges because it's less than 1. Right? Only more than 1 converges. Less than 1 diverges, and this is P is equal to 1/2. So I compared it. Very good. I compared this to P series, and I knew instantly, you know, when I saw the problem. When you have enough experience, when this starts making sense, when you memorize the whole chart, the sheet that I gave you, and you do 5,000 homework problems, right? Eventually you get to that place of Zen when you just open up the entire textbook and you just go down and, you know, for 30, 40 problems, you just say converge, diverge, converge, 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 diverge, diverge, converge, diverge, diverge, converge. You just go through all of them and probably mess up like 1 or 2, you know, out of 30. But you solve all of them like that. It takes time to get there, guys. This is something that you haven't been working with before, so obviously it's all going to be new. And so that's that. That's the divergence test, which can only show divergence. Integral test, where you have to do 3 proofs first. If you have the graph, you can just say, look at the graph, right? But most of the time you don't, so you have to do those calculations. And then if the 3 conditions pass, then if the integral converges, series will converge. If the integral diverges, the series will diverge. And then we have the P series, which is the shortest and simplest and easiest to use. You just compare that. So that's it for this one. Let's go to the break. When we come back, we are going to do about half of the section. We will be talking about root, ratio, and then 2 comparison tests, but probably it's going to be part 1, part 2, because you don't want to stay right forever.